Welcome viewers to the fourth segment of the sixth lecture for the online series of lectures for the course of Algebraic Topology 1. In this segment, we are going to discuss abstract simplicial complex. Okay. In the previous segment, we discussed in detail various aspects of a geometrical simplicial complex. In this segment, we are going to start with the concept of an abstract simplicial complex. An abstract simplicial complex is a collection S of non-empty sets such that if E is an element of S, then every non-empty subset of A is also an element of S. Non-empty subset of A is also an element of S. In other words, the elements of S are closed under subset operations. A subset operation. Okay. So the element A of S is called a simplex of S. Its dimension is one less than the number of its elements, or the cardinality of the set. Okay. All right. Each non-empty subset of A is called a face of A. Face of A. Okay. The dimension of S, we can also talk about the dimension of the abstract simplicial complex. The dimension of the abstract simplicial complex S is the largest dimension of one of its simplices. Okay. Or is infinite if there is no such largest dimension, if there is no such largest dimension. Okay, good. Further, we have the notion of vertex set. The vertex set V of the abstract simplicial complex S is the union of the one point elements or singletons of S. Okay, that's the vertex set. An element V, small v in big V, the vertex set, is called a vertex. Vertex. And the vertex will be considered the same as the zero simplex, the singleton V in the abstract simplicial complex S. Okay. Now a subcollection of S that is itself a complex is called a subcomplex of S. Okay. All right. Now the notion of isomorphism between two abstract simplicial complexes. Two abstract complexes S and tau are said to be isomorphic if there is a bijective correspondence. If there is a bijective correspondence F mapping the vertex set of S, the vertex set of S to that of tau. Tau, such that whenever the set from A0 to AN is an element of this abstract simplicial complex S, well, it holds in both the directions, so we better call it we better phrase it this way. The vertex set of S, so there is a bijective correspondence F mapping the vertex set of S to that of tau such that this element will be in the complex S if and only if uh, now there is another element. This element f of a0 is 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 a vertex in in this complex tau, right? So and so is f of a1 all the way up to f of an. Okay, and this guy is a simplex in the complex tau. Okay, so this is the notion of isomorphism between two abstract simplicial complexes. Okay, now it will be better if we can understand these notions in terms of an example, right? So let us consider um, the example of an abstract simplicial complex. So in order to facilitate um, our understanding, let us draw a picture, although the drawing the picture is not mandatory, but it helps the understanding. So but remember that these, so although we are drawing a geometric simplex here, it does not have anything to do with the with the triangle or the tetrahedron associated with our associated with the notion of geometrical simplices that we have studied earlier. Okay, we don't need them, but it's for our understanding we are drawing this picture. Okay, so uh, we can also label the vertices, okay, by these letters. Okay. Right. So uh, this is the abstract simplicial complex. We have a0, a1, a2. This is a three simplex whose dimension is 2 according to what we discussed a while ago. A0, a1, a2. That's the only two simplex. Right. Right. Okay. So then there is a0, a1. There is a1, a2. There is a0, a2, and then we have a2, a3. Okay. Then we have singletons, right? a0, a1, a2, a3, and finally a4. Okay, the collection of all these sets is called the abstract simplicial complex S. We can check that it's closed under the subset operation. Say if we take this set, then any non-empty subset of this set is also a member of this complex S. Say we say consider a0, a1 is here, a1, a2 is here, a0, a2 is here. The singletons a0, a1, and a2, they are also here. Okay. Um, and so and again we have this this guy here, which is a simplex, right? Which is a one-dimensional simplex. And this guy is a two-dimensional simplex. This is a one-dimensional simplex, and so there are, two non-empty proper subsets, A2 and A3. They are also here. Okay, A4 is here. There is no non-empty proper subset of A4. Okay, so S is an abstract simplicial complex. What is its dimension? Its dimension is, as an abstract simplicial complex, its dimension is 2, because this is the largest simplex in this collection, right? The dimensions of all other simplices in this collection is less than 2. Okay, so the dimension of this abstract simplicial complex is 2. Okay, so well, I'm not drawing it. Nothing is following from this drawing. It is a 2 simplex if you want to look at it as a geometrical simplex, but we are not doing that. So one can start with this abstract set without drawing this picture at all. This is something we have drawn to facilitate our understanding. Okay, so what is the vertex set in this case? The vertex set is the collection of all the one-point sets in the simplicial complex, in the abstract simplicial complex, which means that the vertex set is A0, A1, A2, A3, and A4. This is the vertex set. Okay, note that the vertex set is not a member. The vertex set of the simplicial complex is not a member of this simplicial complex S in general. Okay, and A0, say A1 is a vertex of S. Okay. So so as I have said earlier, that the dimension of this abstract simplicial complex is 2. In this example above, A0, A1, A2 is a subcomplex of S. Good. Now the notion of vertex scheme. Let me erase everything. Vertex scheme. If K is a geometrical simplicial complex, we are writing geometrical as opposed to abstract simplicial complex. Okay, sometimes we just write simplicial complex without mentioning that it's geometrical. It will be, so if I don't write anything in front of simplicial complex, it is implied that it's geometrical complex. And whenever we want to mean abstract simplicial complex, we write it as abstract simplicial complex. Okay, So if K is a geometrical simplicial complex or just simplicial complex, let V be the vertex set of this simplicial complex K. Let calligraphic K be the collection of all subsets A0 to AN of V, okay, such that the vertices A0 to AN span a simplex of K. Okay, so we are given a simplicial complex. Okay, then we know that what are the simplices of this simplicial complex, right? Now we form the vertex set of this simplicial complex, right? And that's just the 1 point sets of this simplicial complex, or the zero simplices to be more precise. Okay, and now as when we identify these vertices, we take the you know the subcollection of vertices that span a simplex of the given complex K. Okay, so this is how we form this collection calligraphic K. The collection K or calligraphic K is called the vertex scheme of this simplicial complex K. Okay, the collection K, calligraphic K, is an example of an abstract simplicial complex. Okay, so associated with the geometrical complex, we can write down an abstract simplicial complex that we are calling vertex scheme of the given geometrical simplicial complex. Okay, I mean that we are noting down a set S where an element of this set will be a set as well, right? It will be a collection of sets here, right? So that each member of this collection will be a simplex in the given geometrical complex K. Okay? So this is the way we construct an abstract simplicial complex out of the given geometric simplicial complex. Okay, good. Now we state our first theorem of this lecture without proving it. Okay, so we emphasize on the understanding of this statement rather than proving it. Theorem 1, we write it here that it's stated without proof every abstract complex S is isomorphic to the vertex scheme, which is also an abstract simplicial complex, but that is associated with some geometrical simplicial complex, to the vertex scheme of some simplicial complex, or if you want to call it geometrical simplicial complex. K. Okay. So there is always such an isomorphism. Okay. This is how you can, relate an abstract simplicial complex um, with a geometrical simplicial complex through the vertex scheme of the underlying geometric simplicial complex. Okay. Okay. Now another result under lemma 2, which is also stated without proofs, states that let K and L be simplicial complexes suppose F is a bijective correspondence between the zero skeleton of these two complexes, between the zero skeletons of these two complexes, or the it's a bijective correspondence between the two vertex sets. Okay, this is a bijective correspondence such that the vertices V0, V1, all the way up to Vn of the complex K span a simplex of K if and only if f of V0 all the way up to f of Vn span a simplex of the simplicial complex L. Okay. So this is the setup. Okay. So if this is the case, then the induced simplicial maps. So we'll define it in a moment. What is a simplicial map? Then the induced simplicial map G between the corresponding underlying spaces. So this is the K mod is the underlying space of K, which is of course a topological space. Okay, and the underlying space of L is given by L mod. So there is a induced simplicial map from K mod to L mod, and that is going to be a homeomorphism. This induced simplicial map G is going to be a homeomorphism. A beautiful result. Okay. All right. So it remains to introduce the concept of a simplicial map, right? And this map G is called a simplicial homeomorphism. It's called simplicial homeomorphism. Homeomorphism or an isomorphism. Isomorphism from K with L. From K to L, or isomorphism of K with L. Of K with L. Okay. Alright. Now the third lemma, which defines a simplicial map. Lemma 3. Simplicial map. Let K and L be simplicial complexes. And F is just a map between the corresponding vertex sets. Okay, be just a map. Suppose that, so in lemma 3 we don't require F to be a bijective correspondence. Okay, observe that it's needed to be just a map. Suppose that whenever the vertices V0, V1 all the way up to Vn of the complex K span a simplex of K, the points f of V0 all the way up to f of Vn will be vertices of a simplex of L, of the complex L. Okay, then this map F can be extended to the entire topological space mod K, can be extended to a continuous map. Okay, so since we're talking about a continuous map, there should be the underlying topological spaces, right? So we can extend F to the continuous map G between the underlying spaces K mod to L mod, such that X being equal to the sum of all Ti Vi's, where I runs from 0 to n, this expression defines a point in the simplex spanned by V0, V1 all the way up to Vn in the complex K. Okay. So it is a point in the simplex spanned by this n geometrically independent points in the complex K. Okay, and so this will imply that g of x is equal to the sum of all the terms ti f of vi, where I runs from 0 to n. Okay, this indicates a point in the simplex spanned by f of v0 all the way up to f of vn in the complex L. Okay, so this thing will imply this thing. Okay, so one calls G the simplicial map induced by the vertex map F, induced by the vertex map F. Okay, good. So now the proof of this lemma is also omitted. Okay, now we have a bunch of definitions again. Definition. So it is guaranteed by theorem 1 that every abstract simplicial complex S is going to be isomorphic isomorphism between two simplicial complexes is already defined, okay, earlier in lemma 2, right? Okay, so that every abstract simplicial complex S is isomorphic with the vertex scheme, which is also an abstract simplicial complex. The vertex scheme resulting of some simplicial complex, some simplicial complex K, we call K our geometric realization of S. Okay, so K is the geometric simplex, right, whose vertex scheme is isomorphic to the abstract simplicial complex S that one starts with. Okay, so now the underlying geometric simplicial complex K is called the geometric realization of S. This is somehow the way how we arrive at the geometric simplicial complex K from the abstract simplicial complex S. Okay, example 1. Suppose we wish to identify a simplicial complex K whose underlying space K mod is homeomorphic to the cylinder, cylinder S1 cross I. Okay. So at this point, it's a good idea to draw the simplicial complex K, which consists of 6 two simplices, 12 one simplices, and 6 zero simplices. Okay, so let me draw the picture. This is K. So so there are two triangles that one can build out of this square. This is C, this is B, this is D, and this is E. And one has this triangle F, this vertex is A, and there is a triangle here and a triangle there. Okay. So one can immediately check that there are 6 two simplices. Okay, 6 triangles. 1, 2, 3, 4, 5, 6. No, I find more. 1, 2, 1, 2, 3, 4, 5, 6, 7. There are 7 two simplices, right? I think there are 7, right? 1, 2, 3, 4, 5, 6, 7. Oh no, these triangles are absent, so there are 6 actually. I beg your pardon. So these triangles are absent. So there are 6. 1, 2, 3, 4, 5, and 6. There are 6 two simplices, and you can check that there are 12 one simplices and there are 6 zero simplices. Okay, and this triangle is, there are 2 different ways of picturing the same complex. So this complex is denoted by K, and there is an equivalent, there is another way of realizing this same simplicial complex, which is L. See that there are three regions first, and then we can construct 6 triangles. So let me label the vertices A, B, C, A, F, D, E, F. Okay. So we attach same levels to some vertices. Okay. So this figure tells us that there are 2 different ways of picturing the same simplicial complex. 2 different ways of picturing the same simplicial complex. Okay. So what we are doing here is that these face is going to be identified with that face here to form this simplicial complex. Okay. Okay. So what is the abstract simplicial complex in this context? This abstract simplicial complex has the following vertex set. S has the following vertex set. V is equal to A, B, C, D, E, and F. Right? It's a 6-element set. While our S, the simplicial complex, is AFD. AFD is AFD is this triangle, and then we have, let us first list all the 2 simplices. ABD is this triangle. Then we have BCD. BCD is this triangle. And then we have CDE, which is this triangle. CDE, following which we have ACE. AC is this triangle, and then we have AEF. AEF is this triangle. Then we have, so these are the 6 possible 2 simplices. Now let us list the 1 simplices. There are 12 such 1 simplices. AF, FD, AD. These are the 1 simplices. Then we have AB, BD, BC, CD, DE, CE, AC, AE, and EF. Okay. So let me count the one simplices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 one simplices. And now let me write down the vertices. A, B, C, D, E, and F. There are 6 such singletons. Okay, together they form this abstract simplicial complex S. Okay, so I need a bit of room, so let me erase this part. Of course, this abstract simplicial complex S is isomorphic. The 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 set that I have erased a while ago is going to be isomorphic to the vertex scheme of the simplicial complex that we have here, the geometrical simplicial complex. Vertex scheme of the simplicial complex K, pictured in figure 3. This is figure 3, right? Good. All right. Now let us denote by F the corresponding maps, the corresponding map between the vertex sets. Okay, so we have, first of all, we have these uh, two pictures of complexes, okay, K and L. So let F be the map that assigns to each vertex of L the corresponding labeled vertex of K. Okay, so under under this map, these two vertices A and F, okay, sorry, these two vertices A, labeled by A, are going to be mapped to the same vertex A here, okay, and these two vertices F here on the right are going to be mapped to the single vertex F here in the complex K. Okay. It is immediate that this F is surjective, right? It is a many to one map. It is not one to one, but it's surjective. Okay. And then F extends to a simplicial map G from L mod to K mod. Okay. This is a simplicial map. This map is continuous. This map is continuous and it is also surjective. Okay, it is surjective. Why? Because F is surjective. Okay, so G is surjective. So this map is extended to this continuous map. Okay, when considered the underlying spaces. Okay, and this map is continuous by lemma 3, right? This is continuous by lemma 3, and it is surjective since F is surjective. Okay, good. And note that both L and both mod L and mod K are compact Hausdorff. Okay. Therefore, this map G is a quotient map. I left it as an exercise for you. It's an easy exercise that you. So one direction follows from the continuity of the map G, and the other direction follows from this condition that both mod K and mod L are compact and Hausdorff. Then use the 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 property of compactness and Hausdorffness to conclude that this map G is a quotient map. Okay, so this map is a quotient map. So I left it as an exercise. Proof, very easy exercise. Now this quotient map G is also called a pasting map. It is also called a pasting map. Okay. Well, it identifies, this pasting map identifies the right edge of L mod L. Okay, let me this map, this pasting map G identifies the right edge of model, okay, this one linearly, okay, linearly since we are dealing with objects embedded in R to the n, right? In this case R to the 3. This map G identifies the right edge of mod L linearly with the left edge of mod L, meaning this one. Okay. Okay, so that's pretty much it. So this is what we wanted to talk about, simplices and simplicial complexes. Now there is this part only left concerning aspects of abelian group that we'll do in the last segment of this sixth lecture. Thank you for attending this fourth segment.